Welcome to homework.
Part A of our question wants us to find the focal length of the lens in this situation. Well, the index of refraction of the glass N is equal to 1.5. One side of the lens is flat and the other side is convex with a radius of curvature of 20 centimeters. So the second side, which I call R sub 2, is equal to negative 20 centimeters since it's convex on the opposite side there. And the other side of the lens is flat, so its radius of curvature, or R1, is equal to infinity. So to find the focal length, 1 over f, we can use the lens maker's equation, which says 1 over f is equal to n minus 1 multiplied by 1 over r1 minus 1 over r2. Well, r1 is infinity, so 1 over infinity is 0. So then we can say that f is equal to the inverse of n minus 1 multiplied by negative 1 over r2. So we plug in the value for r2 as well as the value for n. And all of this is raised to the minus 1 because f was in the numerator, or in the denominator, so we want to get it back to the numerator. So we find that f is equal to 40 centimeters. Which we can box in as our solution for part A. So we'll indicate this as part A. Part B says if an object is placed at 40 centimeters in front of the lens, where is the image located? So we'll get a new page going here for part B. So for part B, it says this, that P is equal to 40. And the units there are centimeters. So we can use the thin lens equation, which says that 1 over the distance to the image, I, plus 1 over the distance to the object, P, which we know now, is equal to 1 over the focal length, which we calculated for part A. So solving for I, we find that I is equal to 1 over F minus 1 over P, all raised to the minus 1. So if we plug in those values, we find that this is equal to 0 to the minus 1. So having a 0 in the denominator gives us a value equal to infinity, which we can box in as our solution